Okay, so we just talked about the fact that we need some quantity that we can get something which is similar to radiation pattern concept, normalized radiation pattern, but quantitative value, meaningful quantitative value. So to start getting those that we're going to later refer to directivity and gain of the antenna, let's start defining a quantity which is radiation intensity, which essentially we try to get rid of the distance. So if you remember in my previous lecture, I wrote the equation for E, R, theta, and phi in the far field zone. So I'm just going to refer to far field as F dot F, far field zone. So in far field zone, you remember we did not have R component, and we note that the R dependency is in the form of e to the power of minus jkr divided by R, and then we ended up having only our angular dependency here, theta and phi, plus e phi naught, theta and phi hat. So if you don't remember that, look at the previous video. So essentially, our dependency is in the form of this, e to the power of minus jkr divided by r. So then I also took the magnitude of E. So this time I'm going to go with magnitude of E squared. So if I do magnitude of E squared, remember magnitude of e to the power of j theta would be 1. So here this is going to be 1. So it's going to be 1r squared. And then here I'm going to have E theta naught, theta and phi squared plus E phi naught, theta and phi squared. So this became my magnitude of E squared. Now, from your course on electromagnetics, you remember that we have something called power density, W. So in my course note, you might also see AV here as subscript. That means time average. So this is the same thing, but for simplicity, I just write it as W equal to half E cross H complex conjugate. So this is essentially power density or Poynting vector. So here I'm just going to write Poynting vector or power density. So this is a very important quantity. So W, first of all, in terms of dimension, is watt per meter square. So this is the dimension of W. So this is watt per meter square. And you can easily see that E is volt per meter, H is amp per meter. So you get volt times amp, which would be watt, and then divided by meter square. So if, as just a reminder, this is the cross product because you have two vectors, and a star is the complex conjugate. This is very similar to the circuit when you learn the power at element. Remember, power became half VI complex conjugate. Now, here E is your V essentially, H is I, both of them are complex conjugate. But here you are dealing with vectors. E and H are vectors, so you're going to have cross product here. And also you're dealing with a space. So in a space, I mean, I'm talking about power density. That would be what matters here. So, and that's why E is volt per meter, amp per meter. So volt, amp, watt divided by meter square. So that's your power density. And this has a direction because cross product of two vector has a direction. If you go to the simulation part, the videos related to simulation software, I'm actually plotting power density vector. And you see that around the antenna, you get a bunch of vectors. It shows where the power is going. So, and this is, again, a watt per meter square. For example, imagine you are receiving this. Imagine this is, maybe this would be a better example. This is a horn antenna, and it has an aperture. Now, another antenna in the space creates some power density. Now, this antenna is collecting that power density with its aperture. So now there is some watt per meter square, and this is now your area here. So when this area is multiplied, maybe effective form of this area, but for simplicity, just assume the physical area for now. When the physical area of this is multiplied by power density, you already had watt per meter square divided by the area of the, multiplied by the area of the antenna. That would be the watt that the antenna is gonna receive. So that's why we have power density, because then we're collecting that power density with some area in terms of meter square. Anyways, this is my power density. Now, I'm talking about far field here. So if I'm talking about far field, I can simplify this, because remember, in the far field, E is perpendicular to H, and they're perpendicular to R hat. So remember, E and H are essentially form a plane wave, as we discussed in the previous lecture. That was our E, that was our H, and that was our R hat. And the other thing that we mentioned was that H magnitude is related to magnitude of E divided by impedance of free space. So when you cross product these two vectors, of course you're going to get R hat component. You're going to be in the direction of R hat. So you can easily see that if you do that, you get your R hat. And because H is related to E using this equation, then essentially, what we have essentially here is that we can simplify this. And if you want to simplify this, you can just write it as W become equal to half. Then you're going to substitute your H with that, and you remember that H would be, E cross H would be in the direction of R hat, so you're going to get an eta naught here, and then you're going to have your magnitude of E squared, and it's going to be in the direction of R hat. So this would be essentially the simplification of that in the far field zone. Remember, this is general, this is just in the far field zone. So in the far field, that would be your power density. As we know, E cross H is R hat, and H and E are related by eta. So we have that. Therefore, I can just say, okay, in the far field zone, this is equal to 1 divided by 2 eta naught E square R hat. So that would be my condition, my simplified equation only in the far field zone. So if I have that, remember I already had magnitude of E squared, so essentially I have my power, so power density. So W becomes 1 divided by 2 eta naught, and now I'm substituting for this from here, which would be R2 E theta naught theta phi squared plus E phi naught theta phi squared. So this would be my power density. And I shouldn't forget the direction, because power density has a direction, and that's my R hat. Now, let me do one trick. I'm going to take this R squared and I'm going to bring it here. So I'm going to call that, of course, going to be R2 times W. That's going to be 1 divided by 2 eta naught, and then the same thing here. Then it's going to be E phi naught theta phi square R hat. Now, if you look at this quantity that I have here, this quantity is essentially doesn't have any R. This is just about the angular dependency of E theta and E phi. I actually have the R square here, and the reason I could do that is that everything is very simple in the far field zone. So this R square is shared by both of them. So I just take it out, and I'm going to have it on the other side. And this is the thing that remains here would be essentially a quantity which is just based on theta and phi, purely angular. And I'm going to refer to this as u theta and phi. So this is going to be u theta and phi. And remember, now I don't have r here. The argument of u is theta and phi. And also, because I already know that this is always r hat, there is no point of making u a vector because I know it is r hat. So I'm just going to take this side and I'm just going to assume that I know things would be in the direction of r hat. So this is my radiation intensity. It's not a vector. It's, as you see, this is that. I put aside r hat. And the other thing that you see here is that this is purely angular. So, and I call this radiation. It's not density, is intensity. Radiation intensity. And I want to emphasize here that again, this is in the far field because the whole derivation is based on the far field. So this is a far field quantity. It's relevant in the far field. Now, what is the dimension of this? So you could easily see the dimension of this by noting that W was my power density. So it was watt per meter square. R square is meter square. So I'm going to get watt. So this is essentially watt. This is the dimension of radiation intensity. So when you look at power density, remember it's watt per meter square. And power density is a vector by definition. Radiation intensity is not a vector because we didn't include vector, it's obvious, and it's also watt. So that's my radiation intensity. Now I have a quantity which is based on theta and phi, it's far field quantity. Now, before continuing with this topic to get to the final goal, which is directivity and gain, let's think about the meaning of u theta and phi for a while, and then we continue. So to think about the meaning of u theta and phi, let me remove this, and I start with an introduction of angle. So I want to remind you about radian definition. So radian is an angle, of course. So radian is defined as follows. Imagine you have a circle of radius r. So you have a circle of radius r, and then you have an angle here, and this angle is subtended by this curve. So this particular angle here is subtended by this curve, and the length of this curve is r. So essentially, you have a circle of radius r, and then you have an angle, and we call these type of angles plane angle because these are essentially 2D angles. They're on a plane. So, but this is the angle that we usually know anyway. So if you have an angle, so whose vertex is at the center of the circle, and it's subtended by arc length, which is r, then we call this 1 radian. That's the definition of radian. So this is 1 radian. Now, if I change it, the same thing, this is radius r, and now this time I have a curve length, which is now 2r. Then this is, of course, 2 radian. And I can just continue like that. And this time I start from here, and that would be my curve coming back all the way. So this is my total length. So the total angle that I'm looking at is this. Now I ask you, what is the total length from here all the way coming back? This is, of course, the circumference of the circle is 2 pi r. So that what would be the total angle here? Would be, of course, 2 pi radian, or 360 as we know it. So this is the definition of angle in plane. We call it plane angle. But we have similar concept in 3D. So imagine you have a cone. Cone is a 3D structure. So if I have a cone, So this is a 3D structure. The angle that I have here would be solid angle. Think of it as 3D structure, not 2D structure, of course. So this would be a solid angle for us. So we call it solid angle. And we also need to define this. So to make it more clear, let me bring a piece of paper and then I can explain this better. So going back to the cone, so imagine you create a piece of cone like this. So imagine, this is bad, but still you can see the concept. So this is essentially the cone. Now the angle that I'm talking about is this angle here. So this angle here. So you see, this is not like a 2D angle anymore, not a plane angle. This is a 3D concept. So this is one cone that I have here. So now if I want to extend the definition of angle, I'm going to go to 3D, and this time I'm going to go to a sphere. So now I have a sphere, and I'm going to be at the center of the sphere. And now here, I was looking at the length of the curve, but now here, I'm going to look at the area of this spherical curvature that I have. So when I start an angle from the center of the sphere, and this angle is subtended by an area on the surface of the sphere, and this area is r square. So the radius of the sphere is r. Then this angle here, which I called solid angle, that's the angle within the cone, that would be one, we call it a steradian, or one steradian. So this is essentially what we have. One steradian would be the angle that you make, the solid angle that you make, that the center, the vertex is at the center of the sphere, and it is subtended by an area of r squared. Now, let's do the same thing that we did for radian. So if I now have an area which is 2r squared, so now if I have a bigger area which is 2r squared, now what would be this angle here? Would be 2 steradian. Now if I do it like a circle for radian, that I cover the whole circle, now if I cover the whole sphere, what is the area of the total sphere? The area of the sphere is 4 pi r squared. So this huge angle here that I have would be 4 pi. So essentially the angle would be 4 pi in this case. So this is going to be the definition of a steradian. Now we could look at this concept and then try to understand something from it. So remember, W is power density. So watt per meter square. It tells you how much watt is passing through 1 meter square. And then you multiply it by R2. So now this means, and this is radiation intensity, this means how much power is passing through R square area. So that's the meaning of that. How much power is passing through R squared area. Now, we already know this is R squared. If this is R squared, let's assume this is R squared. So that essentially means this is the amount of power that's passing through this R squared. That's my U, theta, and phi. That's my U, theta, and phi. And then I already know if the area is R squared, this is essentially a solid angle of 1 steradian. So I can define U, theta, and phi as power per unit solid angle. So it is essentially the power per unit solid angle, because this is going to be the power within this particular cone. So now, if I, for example, if I look at my antenna, I can think of it as so many cone around it. So many cones. These are different cones like that. And within each cone, depending on the angle, I have a u, theta, and phi. So I have so many radiation intensity, and they're just, think of around the environment around the antenna as so many cones, and in each of cone you have a radiation intensity u, theta, and phi. So that's essentially the meaning of u, theta, and phi, a power per unit solid angle. So many cones around the antenna, so I can just keep going, and you're essentially distributing the power within each cone. Now, if you have your main beam in this direction, you have lots of power here. If you have your null in this direction, if you have a cone, you essentially have no power in this particular cone. Now, what would be the total power radiated by the antenna? So what would be the total power radiated by the antenna? That's the question. So total power radiated by the antenna, you need to sum all of these radiation intensity, and summing all of these, that essentially means integration. So you need to integrate them over what? If you want, for example, to find the area under the curve, if this is x, so you integrate this function over dx. So of course here our integration is over element of solid angle. So I call it d omega, a very small solid angle. So the element of solid angle. So I need to integrate my u, theta, and phi over the element of solid angle. Now, what is the element of solid angle? That's the other question that we need to answer. Okay, so how can we find the element of solid angle? So to do that, we need to find what would be a very small surface element on a sphere. So I want to remind you about your course in Foundations of Electromagnetics when you had this type of topic. So imagine this is a very small area on a sphere of radius r. So if you remember what was that, then you can easily find the element of solid angle. So dA, a small piece of area, if you remember, was r2 sine theta d theta d phi. And in terms of dimension, it makes sense, right? Because area is meter square, and you get your meter square here too. So if I wanted to write that in a way that probably makes more sense, it's essentially r sine theta d theta times r d phi. And then when you multiply them, you get this. So they're the same thing, but that's essentially the derivation of this. So if you don't remember that, review this or ask me. And so this would be the area, an element of an area on a sphere. Okay, we have now the element of area. So this was our element of area. Now, if we want to go to solid angle, so you know that you always need to divide by r squared. Remember, if this was, for example, r squared, then a radiant was r squared divided by r squared, 1 radian. Now, if you have an area which is that, you want to find the solid angle, you divide by r squared. So if you divide dA by r squared, you get sine theta d theta d phi. And this is your solid angle in terms of a radian. But because you started with something, a tiny area, that would be the element of solid angle, which we call it d omega, a tiny one. So this is our d omega. So if you want to find the total power radiated by the antenna, you essentially gonna substitute this here, sine theta, d theta, d phi, and you can integrate that and find the total power radiated by the antenna. Now, as an example, let's consider, for example, radiation intensity of an antenna be A naught sine theta. A naught is just a value. I mean, it can be anything for now, but let's assume it's A naught sine theta, and the purpose is to find the total power radiated by the antenna. First of all, you realize that if this is my axis, this radiation intensity doesn't depend on phi. So phi means you, for example, assume that you are in the xy plane and you're just going around. This is changing phi, because if you are in the xy plane, your theta is 90. Your theta is 90 and you're just changing your phi. And this does not depend on phi. That means that if you go from here to here to here to here and so on, you see the same thing. So that becomes exactly like our dipole antenna. If that was my dipole antenna, if I go around it, because of symmetry, I see the same thing. So this is the same type of antenna. The other thing you can see from here is that the maximum radiation happened at theta equal 90. So theta equal 90 means you are in the xy plane. And that's also consistent with what we had for dipole antenna, that if this is z-axis, maximum radiation is perpendicular to that theta 90. And also in theta equals 0 and 180, radiation intensity is 0. That means in that cone, there is no power. So theta equals 0 means along the z-axis, theta equal 180 means negative z-axis. So in this situation, we essentially get no power in the plus z and minus z, and that's also consistent with our dipole, that along the axis of the dipole, we had no radiation. So these are some insight into that. Now, if you want to get the total power that this antenna radiates, you're just going to say, okay, I'm going to have u theta and phi, which is A naught sine theta, and I'm going to integrate over the element of solid angle d omega. But d omega is sine theta d theta d phi. Now you see that's a double integration from theta and phi. So theta varies from 0 to pi, phi varies from 0 to 2 pi. So this is what we have. As you see, the integrand doesn't have any phi dependency, so it's easier to first integrate over phi, so which is going to be simply 2 pi. So I'm going to have 2 pi, then the integrand, and I can't take A naught out, and the integrand over theta remain. So that would be my integrand, and if you substitute sine a square with 1 minus cos 2 theta divided by 2 d theta from 0 to pi, then you can easily perform your integration, and that becomes half theta, and that becomes minus 1 divided by 4 sine 2 theta, and this is from 0 to pi. So this is, and then if you calculate that, you get 2 pi A naught. This becomes pi divided by 2, and this becomes 0. So you don't have that anymore. So 2 and 2 cancel. You get pi squared A naught. That would be the total power, and the dimension is, of course, watt. So that's the total power that your antenna radiates. One common mistake that I've seen in this calculation, which you should be careful when you are calculating this type of thing. You see, radiation density depends on angle, but total power is the integration over these angles. So when you integrate over the angle, the final result cannot have, for example, an angle here, because that's the total power. If you have at the end something like sine theta, you know that you've done something wrong. So that would be our radiation intensity in this case, that the total power that we have. Now let's see how we can make these how we can take advantage of this to create a quantity that's similar to radiation pattern, but now it has quantitative value, meaningful quantitative value. So to do that, we're gonna compare the performance of the radiation intensity for an antenna with the radiation intensity of a hypothetical antenna, which is isotropic antenna, if you remember from one of my previous video. So isotropic antenna is a hypothetical antenna. It doesn't exist, and it radiates the power identically everywhere. So that essentially means if the power in all the cones are exactly the same. So essentially that means u, theta, and phi for the hypothetical antenna, isotropic antenna, is constant. So it radiates the power exactly the same. So now what would be u, theta, and phi of an isotropic antenna? So you essentially say, okay, what is the total power that the isotropic antenna radiates? So total power. And now you need to equally distribute that between all these solid angles. Now, how much total solid angle we have on a sphere? Remember how much total angle we had on a circle? 2 pi. How much total angle we had on a sphere? 4 pi. So that's essentially total power divided by 4 pi. That's going to distribute the total power equally in all these cones around the isotropic antenna. So that would be the u, theta, and phi of an isotropic antenna. So now we're gonna also use that in our approach. So I'm gonna say, let's define a quantity called directivity. So this is my directivity, and directivity is defined as a ratio. So you're comparing two things. There is a numerator and there is a denominator. So what you are comparing, the u, theta, and phi of your antenna. So you have an antenna, there is a u, theta, and phi associated with the antenna. And then you are comparing it with the u, theta, and phi of an isotropic antenna, assuming that that isotropic antenna radiating the same amount of power that your antenna is radiating. So imagine your antenna radiates in total 1 watt, and you have a radiation intensity. And then when you want to compare it to an isotropic antenna, you say, okay, would be u, theta, and phi of my antenna divided by u, theta, and phi of an isotropic antenna. But as soon as you put isotropic antenna here, you need to write its radiation intensity. And radiation intensity of isotropic is total power divided by 4 pi. And it does not depend on theta and phi, so I can just remove that because it's isotropic. You just say u isotropic. But the question is, when you want to plug u of isotropic, what would you plot for total power? So for directivity, you essentially plug the same total radiated power that's being radiated by your antenna. So here, instead of total power divided by 4 pi, I'm now going to say P radiated by my antenna divided by 4 pi. So now I'm comparing these two things. So you can say that directivity is the ratio of the radiation intensity u theta and phi to the radiation intensity that would be obtained if the total power radiated by the antenna were radiated isotropically. So if you look at this definition, we say ratio of u theta and phi, which is this, which is the numerator, divided by the radiation intensity that would be obtained if the total power radiated by the antenna were radiated isotropically. This big sentence is essentially the denominator. So that essentially means compare the radiation intensity of your antenna with the radiation intensity of an isotropic antenna. Now, radiation intensity of isotropic antenna is this, total power divided by 4 pi. Now, the question is what you're going to put for total power. Then directivity says, assume the total power radiated by your own antenna. So that would be P radiated divided by 4 pi. Now, usually we don't write this like that, so we write it as 4 pi u theta and phi divided by P radiated. So that would be the definition of directivity. And as you see, directivity is also a function of theta and phi. So that's essentially the definition of directivity. So when you look at that, now let's make an example. If now, in terms of the conceptual meaning of directivity, let's consider that for a second. So if, for example, the maximum directivity for an antenna is, let's say, 3 dB, and then for a different antenna we have maybe 10 dB maximum directivity. So what does that mean? That essentially means the first antenna, maybe antenna A, in its maximum radiation direction, it accentuates the power 3 dB more than what an isotropic antenna can do. So 3 dB more, because isotropic antenna is a hypothetical antenna that radiates equally in all directions. Now, antenna A does a better job compared to isotropic antenna in the direction of maximum radiation by 3 dB. It does a better job by 3 dB. Now, antenna B, and remember 3 dB means double. So in terms, if you don't want to use dB scale, that means it in terms of radiation is 2 times more than isotropic antenna. But remember, when you radiate in one direction 3 dB more than isotropic antenna, in other direction you're going to radiate less than isotropic antenna, because this antenna, we're assuming they're passive. They cannot generate power for you. Whatever power you give them, they're going to use it. So when you radiate in one direction 3 dB more, in other direction you radiate less, and that's why you have nulls and side lobes and so on. Now, antenna B, compared to isotropic antenna, it radiates 10 dB more in the direction of maximum radiation. So now you can compare them. This is 3 dB more, this is 10 dB more. And now you can, so these numbers are very meaningful. You're comparing it with a standard. And what is the standard here? Is isotropic antenna. And what you are dividing is the radiated power by the antenna that you are testing. For example, for antenna number A, you're dividing by the P radiated by antenna A. For antenna B, you're radiating by the antenna, by the radiated power by antenna B. So the effect of the power that you're giving to the antenna is already canceled, because one antenna may radiate 1 watt, the other one may radiate 100 watt. That doesn't matter, because in this ratio, the effect of the actual value of power is gone. It's not important. This is the ratio that is important. You're comparing your antenna with an isotropic antenna under the same power for your antenna. So essentially, you don't need to say this is the amount of power that I given to the antenna, because this is the ratio and this is being canceled here. So this is the directivity, and usually directivity is expressed in terms of dB, but if you want to do that, of course, you need to take 10 log base 10. But then also sometimes instead of dB, some people might write it as dBi, and this small I here means it's a dB, but then it's been done in a comparison with isotropic antenna. So this is dBi. And the other thing that you see here, I said maximum directivity. So sometimes people just report maximum directivity. So if you want to report maximum directivity, you usually write it by D naught, which naught here is for maximum. And because this is supposed to be maximum, then you need to have 4 pi U max divided by P rad. And that becomes maximum directivity in this case.